but not quite exclusively. So the rectangular coordinate system consists of three axes that are at right angles to one another. Now, all of the coordinate systems that we're going to study consist of three axes at right angles to one another. The rectangular coordinate system is special in that the axes do not move as the point moves around in space. So the directions specified by the X, Y, and Z directions are fixed and do not change as the point moves around. Usually, we use what is called a right-handed coordinate system. An example of which is this. The X direction, the Y direction, and the Z direction. And I drew just the positive axes for X, Y, and Z. Why is it called a right-handed system? Because if I take my right hand and I put my fingers in the direction of the x-axis and then curl my hand around towards the y direction, my thumb points at z. So the triad is always x, y, z in that order. However, if I put my fingers of my right hand along the y-axis and then turn my fingers into the z-axis, my thumb points around along x. So y, z, x. And you probably will guess that if I put my fingers along the z-axis and curl them into the x-axis, I get my thumb pointing in the y direction. So it's always x, y, z, y, z, x, or z, x, y. Now you can have a left-handed coordinate system by doing the same darn thing with your left hand. And I think that's the way they do it in Britain, but it has something to do with the way they drive or something. Okay, so that's the rectangular coordinate system. Now we specify, well, you know what? I'm going to talk about vectors in general more. Let's talk about coordinate systems first. So I can specify a point in space by specifying the x coordinate, the y coordinate, and the z coordinate. And I can write them as a triad in parentheses in the order x, y, and z. All right, now the other coordinate system, another coordinate system that we will frequently use is the polar coordinate system. And the polar coordinate system is a two-dimensional system. So right and left-handedness has no meaning. It's customary to draw a plane for this two-dimensional system as x and y coordinates. Z would be in and out of the board, but it's only a two-dimensional system. So for two-dimensional problems, a point in this space can be described as the x and y coordinates, but it can also be described in another way. Draw a line from the origin to the point in question, and the length of that line I'm going to call r for radius, but remember it's two-dimensional, not three-dimensional. So it's just the radius in the xy plane, and I can specify an angle, which is usually given by theta or phi. Let's go ahead and say theta. And that angle is measured by convention from the positive x-axis. So let's say this point is given by 12 and a y value of 5. How can I express that in polar coordinates? Well, the distance from the origin to this point can be determined by the Pythagorean theorem. So r is just equal to the square root of 12 squared plus 5 squared. You already know this. So this is a right triangle with the x distance being here and the y distance being here. So obviously r is given by the square root of x squared plus y squared. Now what about the angle? Well, the angle theta is given by the tangent of theta is equal to y divided by x. And you can see this theta, I may have mislabeled this here. That is the angle theta right there. And it's measured positive from the positive x-axis. If it goes the other way, it's a negative angle theta. All right, obviously the tangent of that angle is y over x. So if I know y and I know x, I ought to be able to figure out what theta is. In fact, I can plug it into my calculator. Theta equals the arc tangent, and I'm going to write it as tangent minus 1. That means the inverse tangent or the arc tangent. It doesn't mean 1 over the tangent. You can write arctan if you prefer, of y over x. So I'm going to put that in my calculator. First, I'm going to make sure that my mode is set to degrees. So I want the arc tangent of 5 divided by 12. I get 22.6 degrees. So in this case, my theta is equal to 22.6 degrees. Now you can set your calculator to be either degrees or radians. And it is natural, and it will sometimes be necessary to use radians. However, when I have a choice between radians and degrees, I always choose degrees just because I intuitively know what 22.6 degrees looks like. So if I were to write down for you, okay, what kind of angle is 6.7 radians? Not so intuitive what that means, is it? So I like to work in degrees. Okay, now, however, there's a problem here. Let's do another problem like this. So let's determine the angle for this point. In which case that angle is given by this. And let's say this point represents, let's see, x is negative, so let's just call it negative 12, positive 5. So let's take the arctangent of that. The arctangent of minus 12 divided by 5. And I get minus 67.4 degrees. So my red angle theta is minus, what did I say, 67.4. Well, that's obviously not right, isn't it? I mean, first of all, it's a positive angle, not a negative angle. But it's clearly in the wrong quadrant. My point is here in the second quadrant, but the calculator tells me it's down here in the fourth quadrant. So something's wrong. And what is it? And what's wrong is this. The tangent is a multiple valued function. That means if I have an angle theta, let's say this space here just as a graphic representation of all the possible angles theta, and this is the representation of all the possible tangents of theta, I would have a mapping in which different angles give me the exact same tangent because of the circularity of what are called the circular functions. The cosine, sine, tangent, okay? Those are called the circular functions. So because of their circularity, the tangent of theta is multiple valued. That means, I'm sorry, I've said that wrong. The tangent of theta is an onto mapping. Because I get more than one angle theta can give me the exact same tangent. That is a totally acceptable function. There's no problem with that. But going back the other way, it's multiple valued. So I take a number that is the tangent of theta, and I have an infinite number of possible thetas that will give me that tangent. So it doesn't work. It's not a real function. For that reason, your calculator, by convention, restricts the value of theta between degrees plus 90 degrees and minus 90 degrees. Okay. So that means that you, no matter what number you put in, the calculator is going to give you something between minus 90 and 90. If you set it on degrees. Minus So what about things in the second and third quadrants? Well, you have to know by looking at the numbers what quadrant you are in. And if you are in the first, okay, tell me I did this right. First, second, third, and fourth quadrants. Everybody agree with that? Okay. If you are in the first or fourth quadrant, you will know that simply looking at the numbers for the XY coordinates. Now, calculators give you the right answer between minus 90 and 90. Of course, there are an infinite number of answers, but you want the one between minus 90. If you are in the second or third quadrants, what you're going to get is a number that is 180 degrees off. So this 64.7 is actually that point right there, or that angle right here. So what do you have to do? What do you do, Michelle? I see you smiling, so you must know all about this. So what do you do?
So sorry, right there. I'm so sorry.
It's okay.
You would.
It's okay.
So you would. All of it would become negative.
Okay, here's how you fix it. Or Tuan, do you know?
Do you like add 180?
There you go. Yes. So if you are in either the second or third quadrants, and you know by looking at the number, you simply add 180 degrees, or equivalently subtract 180, because going this way 180 takes you to the exact same place as going this way. But if you add 180, you end up something between let's see, if you add one, you'll end up with a positive number. Doesn't matter which way you go. The angles are the same. So if you take the minus 67.4 and add 180, we get 112.6. So this angle right here is 112.6 degrees. Okay, is everybody okay with the ambiguity of the arctangent? You won't have this problem with the other circular functions because for physical reasons, the arc sine and the arc cosine are always going to give you numbers that will make sense physically. You don't worry about that ambiguity. But for the arctangent, there's an ambiguity when you're going from rectangular to polar coordinates. Okay, so that's polar coordinates. Now, cylindrical coordinates are polar coordinates in which you simply add the z-axis. So, in polar coordinates, you will state r and theta. In cylindrical coordinates, you'll state r, theta, and z. So all you're doing is adding one rectangular coordinate to the xy plane, which we conventionally call z. Now, for any of this to work, you have to define where the x-axis is because the angle theta is measured from the x-axis. So that has to be defined. But you define that for yourself based upon the physics of the problem, where you want to put it. That's cylindrical. Now, spherical coordinates are a little different. They are actually the one that is generally the most complicated. So let's draw our x, y, z axes here. I'm only going to draw the positive x-axis, but I've drawn the positive and negative for the others. So that's to try to make the picture easier to understand. So here's my right-handed XYZ. Okay, now a point in three-dimensional space is going to be given in spherical coordinates by the distance from the origin to the point as our first variable, or our first coordinate, I should say. That will be r. Notice that r is not the same as polar and cylindrical. Sometimes rho is used for spherical for that reason, just to keep them separate. But we're going to just use r because it's intuitive. It's the actual radius of that point in three-dimensional space. It does not lie in the xy plane, and it does not lie in the yz plane necessarily. It could be any point in space. So that r is the distance from the origin to the point. Now, the first angle that is used in spherical coordinates is called the zenith angle. Conventionally, we use theta for the zenith. People use different angles. I'm going to use theta for the zenith. What is that? That is the angle between a line that represents this radius vector and the z-axis. And notice that this line could be anywhere on a cone and have the same zenith angle, which would then be called the cone angle. All right, so I need one more coordinate. And the one I use is called the azimuth. I drop a perpendicular to the XY plane. So this point is out in space, but I drop a perpendicular to the plane down to the XY plane. And let's say that pierces the XY plane right here. I draw a line from the origin in the XY plane to that point, and the angle from the positive x-axis is called the azimuth angle. And conventionally, we give that the symbol phi. So it's much more complicated. It's easy to go from polar and cylindrical to rectangular and back and forth. It's a little more complicated in spherical coordinates. I don't think we're going to do any transformations. If we do, we'll go over them. But I think it's just important that you understand how these angles are defined. And the problems that you're given that use cylindrical and spherical coordinates will generally be sufficiently simple that you can draw yourself a picture and figure it out, so long as you understand the definitions. Let's go back to rectangular for a moment. Now, what if I have a little volume surrounding this point? So a little box. And that little box has sides dx, dy, and dz, where those are differentials. So you could say that they are delta x, delta y, and delta z if they're tiny little pieces. Or you can say, in the calculus manner, they're infinitesimal. The infinitesimal volume in rectangular coordinates is just dx, dy, dz. So for example, if I have some volume in rectangular coordinates out here defined, the volume of that is simply going to be the integral over this region, dx, dy, and dz, where this first integral is by convention is over the x, second over the y, the third here outside of the z. So you usually evaluate these multiple integrals from inside to outside, and you evaluate them in the same manner as you would a single integral in terms of determining the antiderivative. Now you may have, in this example, you don't have a function in here. All you have is a volume over which you're integrating. But if you had a function in here, then when you integrate with respect to x, y and z are held constant. When you integrate with respect to y, x and z are held constant. And when you integrate with respect to z, x and y are held constant. I think I said that right. We're going to do examples of this, so don't worry about it. And we're only going to do some simple things. In determining moments of inertia and centers of mass and things like that, we're going to be doing these kinds of integrals, but we're going to do simple ones. And you'll see exactly how it works without any problem. But the important point is that there is a little differential volume over which I can integrate. Now, in polar coordinates, of course, I don't have a dv because it's a two-dimensional space, but I have a little differential area. And, you know, I think I can write it on this. So here is a little piece d theta, and here is a little piece dr. So this little differential angle here is d theta. I drew it as a negative, but that's okay, it doesn't matter. And then this little piece here going out is dr. So what would be the differential area? Well, one side of this little square is dr, and the other side is r times d theta. So in terms of the radian measure of an angle theta, theta is equal to the arc length over the radius, right? Theta equals s over r. That means that s is equal to r d theta. That means that my differential area dA is r dr d theta. And you can write it any way you want, but it's conventional to write the r inside so that when you do the integral, you don't forget to include the r. So I could integrate this this differential area over something and get what the area is. In fact, let's do it for a circle because a circle is really easy. So I want to know the area of a circle. Well, the area of a circle is the integral over theta and r of dA, which is equal to the integral r dr d theta. Now, for a circle, what are the limits of integration on r? There's 0 to the radius big R of the circle. And what are the limits on theta? Well, I'm going all the way around the circle, so my limits of integration are 0 to 2 pi. So let's do this inner integral first. I get 1/2 r squared. Evaluate that between 0 and r, and that becomes 1/2 big R squared. Now I have the integral from 0 to 2 pi d theta. Notice in the integral with respect to theta, r is held constant. So what is the antiderivative d theta? It's just theta. Theta evaluated between 0 and 2 pi is just 2 pi. So my answer for the area is 1/2 big R squared times 2 pi, which gives me pi r squared, which you already know is the area of a circle. So that was a really simple example of how this works. Now in cylindrical coordinates, here, right down here in the corner, it's obvious. dV must equal r dr d theta dz, because all I've done is add the rectangular z component. And now I've just got a 3-dimensional integral in r, theta, and z for polar coordinates. However, for spherical coordinates, it's more complicated. And dV in spherical coordinates is r squared times the sine of theta dr d theta d phi. So if I wanted to determine the volume of a sphere, so the volume of a sphere is equal to a 3-dimensional integral r squared sine theta dr d theta d phi. And my r coordinates go from 0 to the radius of the sphere. Theta, what are the limits of theta? The zenith angle is between 0 and pi, isn't it? The way I've defined it here, I've not defined it as pi on 2 and minus pi on 2. When it's straight up, theta is 0. And when the point is straight down along the z-axis, theta is pi. And then the azimuth goes all the way around. 0 to 2 pi. Now, do the integration with respect to r, holding sine theta as if it were a constant. Do the integration with respect to theta, and then do the integration with respect to phi. And your answer, if you do it correctly, had better be 4/3 pi r cubed. And you can see where the r cubed comes from. What's the antiderivative of r squared? It's 1/3 r cubed. So I'll let you work that out for fun, but we'll do a whole bunch of these, so you'll see them in glorious detail. This is a little bit outside what you might be used to because you probably don't have your multivariable calculus yet. So this might be new. So I understand. I'm giving you a little bit at a time, and when we get to the point where we're going to use this information, we've got a lot of good examples, and you'll see how it works. It's very simple.
Professor?
All right. Yes.
Yeah, could you explain one more time why the theta angle is, the range is from 0 to pi and not 0 to 2 pi?
Because straight up is theta equals 0, and straight down is this angle, which is pi, and that's it. It's the azimuth that goes all the way around. But you can, as far as zenith is concerned, you can only be straight up or straight down or somewhere in between. So if you were over here somewhere, the zenith angle would still be between 0 and pi. It's the azimuth that would go around. It's hard to visualize, isn't it? First time you see it. Okay, you're good?
Yeah, so basically this theta angle will always be from 0 to pi?
Exactly. That'll be the maximum extent. Depending upon what you're integrating, the shape over which you're integrating, it could have different limits. But the maximum limits it can have would be from 0 to pi. So if you're integrating over a sphere, you're going over the maximum of all of these. Okay. So now that we know a little bit about coordinate systems, let's discuss vectors, because we'll be describing vectors in terms of these coordinate systems. Actually, we will primarily work with rectangular systems. Thank goodness, right? Okay, so let's discuss what a vector is. Omar, can you tell me what a vector is?
I believe a vector, from what I remember, is movement like space, I think.
Okay, it's actually very simple. A vector is a mathematical quantity which we use to describe physical things, but it's a mathematical construct. And it has two attributes. It has a magnitude and it has a spatial direction. It's very important. It has a direction in space. So velocity is an example of a vector. The magnitude of the vector, of the velocity vector, is, what do you think, Adam? What's the magnitude of a velocity vector? We have a name for it.
The what of it?
The magnitude of velocity, we have a name for it.
Is it speed?
Speed, exactly. Exactly. Speed is a scalar quantity. A scalar quantity is a physical quantity that only has a size, a magnitude, we call it. A vector has both a magnitude and a direction. So, you know the joke about the airline pilot who says to the passengers, I've got good news and I've got bad news. The bad news is I have no direction. I have no idea what direction we're going. The good news is we're making excellent time. So what he's saying is he's going really fast. He just doesn't know what direction he's going. So he knows his speed, but he doesn't know his velocity. So an example of velocity would be to say, I'm going 20 miles per hour in that direction. And you specify the direction somehow, due north or something. Speed is merely the magnitude of velocity. Okay, so that's the difference between a vector and a scalar. Scalars have magnitude, vectors have magnitude and a spatial direction. So for example, let's do a one-dimensional problem here. This just signifies the origin. Here's my x-axis. Here is x1, my initial position. Here is x2, my final position. My displacement, delta x, is a vector. And it equals x2 minus x1. Now I have to specify how I know direction in rectangular coordinates. So what I need to do is define a unit vector in the positive x direction. So I've got a little vector whose magnitude is 1. And since we're talking about displacement, it's 1 meter because of the MKS system. And I signify a vector that's a unit vector that just tells me direction with a little hat on it. So I could write this vector this way. Now with one-dimensional problems, you don't have to worry about all this kind of stuff because in one dimension, it's either going to be a negative or a positive number. And if it's a positive number, it's in the direction of the positive x-axis. And if it's a negative number, it's in the direction of the negative x-axis. When you go to 2 and 3 dimensions, you have to use the unit vector notation, and we'll talk more about that. Oh, and you may not have seen this before. I put a little arrow over my delta x, and that indicates that delta x is a vector. It's called displacement, or the displacement vector. In this case, my displacement vector, x2 minus x1, obviously x2 minus x1 is a positive number. And my displacement is therefore in the positive x direction, going from x1 to x2. So the magnitude is x2 minus x1, and the direction goes from the initial position to the final position. And the math works out if you define it as x2 minus x1. Okay, that's pretty easy. That's displacement. Now, in one dimension. Okay, let me ask you this question. What about a quantity delta t, where delta t is a time interval? So my delta t could be from 1 second, t equals 1 second, to t equals 2 seconds. Or I could have my delta t defined as backwards in time. There's no reason why not, although it may seem strange. The laws of physics actually work backwards in time. So I could say that my time interval goes from t equals 2 seconds to t equals 1 second. In which case it would have a negative delta t. So my question to Daniel is delta t a vector?
No, it would be a scalar, right?
It's a scalar. Why?
I'm not sure why.
The answer is actually very simple. It goes back to the definition. A vector has a magnitude and a direction in space. Does delta t have a spatial direction?
No, since it's just time, so it
That's
would.
exactly right. That's exactly right. So negative delta t versus positive delta t, that's fine. Put a negative sign, put a positive sign, go backwards, go forwards, doesn't matter. But that does not signify a direction in space. So delta t is not a vector. So it's very important. A vector has a magnitude and a spatial direction. Okay, not a direction on an arbitrary axis like a time axis or something like that. Okay, so that's the idea of a vector. Now, let's see, displacement is a vector. Velocity v is also a vector. It is defined, actually the average v, I'm going to define first, as delta x, which is a vector, over delta t, which is a scalar. So a vector divided by a vector makes no sense. So delta t can't be a vector. Otherwise, velocity would be nonsense. So we've got a scalar here divided into a vector. That's totally acceptable. Give me another vector. Okay. So what are some other vectors that we will study this semester? Well, we will study momentum. Momentum is equal to mass times the velocity vector. Mass is a scalar, so I can multiply a vector by a scalar, no problem. We will also study, in fact, before we get to momentum, we'll study force. Force is m times a. A is acceleration. It is a vector. It's the rate of change of velocity. Since velocity is a vector, obviously acceleration is a vector. We'll look at things like angular momentum and torque, which are defined in a more complicated way that we'll get to in a moment. So those are the kinds of things that we'll study in terms of vectors. Now, in rectangular coordinates, I can specify a vector in a couple of different ways. So here is my x, y, z coordinates. I define mathematically in this space, I define my vector as having the tail at the origin and the head at a certain point in space. And it's customary to draw it this way. So this point in space, I can specify as x, y, and z. I can specify the vector as being the quantity, the vector whose tail is at the origin, whose head is here at the point. So the magnitude of the vector is the length of this arrow. So let's call this vector A. And the magnitude of A is just the square root of x squared plus y squared plus z squared by repeated application of the Pythagorean theorem. You might as well just memorize it. What about its direction? Well, I can specify its direction in a lot of ways. I can specify it in spherical coordinates or cylindrical or anything else. But in rectangular coordinates, the way I write the vector A is the x component of A, and I should have written this as A sub x, A sub y, and A sub z. That's what I mean. A sub x times the unit vector in the x direction plus the vector A sub y in the y direction plus A sub z in the z direction. And you can use hats on x, y, and z in order to indicate the unit vectors in those directions. So my unit vector in the x direction is this. My unit vector in the y direction, it has a magnitude of 1 along the y-axis, and this is the unit vector in the z direction. So in order to get this component of the vector, I take the x coordinate and simply multiply it by this unit vector. Then I add that to the y component, which is multiplied by the unit vector in the y direction, and so on. Okay. Now it's actually customary to write this in another way, which you can do, either one, whichever makes you happy. A sub x times I plus A sub y times j plus A sub z times k. So the unit vectors in the x, y, and z directions you will frequently find by convention are just called I, j, and k. You can call them x, y, and z with hats if you want. It's entirely up to you. All right, so that's a vector in rectangular coordinates. And the magnitude of this vector is just going to be, from the Pythagorean theorem, the square root of the sum of the squares of its components in rectangular coordinates. Now you will have some problems in which you will be given data in terms of compass directions. And in 2 dimensions, of course, it only makes sense for compass directions. So let's call it the XY plane. So X and Y. Now, conventionally, we're going to call this north, this south, this east, and this west. No, we're not. West, east. There we go. God. Okay. They do this just to confuse you and to make sure that you visualize vectors correctly in 2 dimensions and you can figure out what's going on. So there'll be problems like an airplane flies 10 kilometers due north. Then it flies 15 kilometers north of east. Then it flies so many kilometers to the south of west. All right. Well, no, I don't have, oh darn. Okay, I'll have to draw them. this direction right here is 45 degrees. Actually, I should have written it down here. Is 45 degrees north of east. That's what that means when you see that. What about this direction here, where, let's say this is 10 degrees. That would be 10 degrees to the south of west. Okay? Here's a direction where this right here is 70 degrees. So Louis Cornejo, how would you describe that in terms of compass directions?
Sorry, can you repeat that?
Yes, how would you describe this direction right here, where this angle is 70 degrees, in terms of the compass directions?
Southeast, but closer to south.
Well, you can describe it precisely. You can say 7 degrees south of east. So south of east means start going in the east direction and then move towards the south 70 degrees, and that's your direction. Obviously, that would be the same thing as 20 degrees east of south, but nobody says it that way. So you'll have some problems in mastering physics where they're going to give you complicated directions in terms of this stuff. And what you are expected to do is to resolve these directions in terms of X and Y components for an XY coordinate system. So X and Y. So let's say this is 15 kilometers. How would you describe that vector? And we can do it with unit vector notation, or we can do it as an ordered pair where X comes first. So for simplicity, I'm going to write it as an ordered pair. Well, what is the X component here? It's 15 kilometers times 45 degrees, cosine of 45 degrees. So 15 kilometers times the cosine of 45 degrees. And what is the Y coordinate? Well, that's 15 kilometers times the sine of 45 degrees. So now you've got it in terms of rectangular vector. What about this one down here that's 70 degrees south of east? Well, the X component here is going to be what? Well, let's say this is 10 kilometers. It's going to be 10, I'm going to suppress the kilometers, it's understood, times cosine, not of 70, but of minus 70 degrees, right? Because you're measuring that as minus 70 degrees. And Y is going to be 10 times the sine of minus 70 degrees. The cosine of minus 70 degrees is a positive number. The sine of minus 70 degrees is a negative number, as it darn well better be. Okay, so you can take all these stupid vectors in terms of these compass directions and put them in terms of X, Y coordinates, and then do whatever you need to do using vector notation. So, how do you manipulate vectors? Well, how do you add vectors? Well, you add vectors by adding components. So let's say that vector A is equal to A sub xi plus A sub yj plus A sub z in the k direction. And let's say vector B is B sub x in the I direction plus B sub y in the j direction plus B sub z in the k direction. Then A plus B is just AX plus BX in the I direction plus AY plus BY in the j direction plus AZ plus BZ in the k direction. And any of these components could in principle be 0, right? You could have vector B restricted to the xy plane, in which case B sub z would be 0, and that's fine. No problem. So that's how you add vectors. You add them component-wise. Now, you can add them geometrically. Let's visualize this. Here's X and here's Y. And let's say that A was this vector. And B is that vector. Now let's not make it quite so extreme. There we go, that's B. Well, adding them component-wise is equivalent to taking B and putting the tail of B at the head of Y and just moving it like that. And now the resultant is from the origin to the head of B. So let's say that the A and B represents displacements. I go from the origin to the point given by vector A, and then from that point, I go to the point given by vector B by putting the tail of B at the head of A. My resultant is just adding them together geometrically. And of course, it works in 3 dimensions as well, even though I drew it in 2. Okay, so that's addition of vectors. Now, vector multiplication is more complicated. And vector division doesn't mean anything. Okay, I have actually 3 choices. I can multiply a vector by a scalar. An example would be, let's let A equal A sub x in the I direction plus a sub y in the j direction plus the k component in the z direction, and I wrote k and I meant to write z. This is a little cumbersome, isn't it? Okay. I can multiply that by a scalar this way. I can take a scalar number like 10 and multiply a by it. And what I will get is a times a sub x in the I direction plus a times a sub y in the j direction plus a times a sub z in the k direction. So all I've done is lengthen the vector by a factor a. If the magnitude was 10 and a is equal to 5, then the magnitude of the new vector is 50. Easy. Now, there is another kind of multiplication called scalar multiplication. It's not the same thing. I mean something different, even though the words sound very similar. Okay, in scalar multiplication, I multiply two vectors, but the result of the scalar multiplication is a scalar number, not a vector. So for example, A multiplied by B is going to be A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z. That is the scalar product, or sometimes called the dot product, because I use a little dot to indicate it. So the scalar product of two vectors gives me a scalar, not a vector. In physics, we have a bunch of examples. Here's an easy one. Work is a scalar. It is defined as the vector force dotted with the vector displacement. So that's an example of a scalar product in physics. Another way to write this is to write the absolute value of A, and I'm going to suppress the absolute value bars. If I write A without the vector sign, I mean the magnitude of A. So A, a scalar number, times B, a scalar number, so the magnitudes of these two, times the cosine of the angle between them. So if I have A here and B here, that is the angle that I mean. That angle will exist in the plane defined by A and B, but it won't be the polar coordinate theta, because A and B are in 3 dimensions. So they could be pointed in any old direction and form a plane that is in any direction. So theta is the angle between the two. Now, if I were to give you on a test and a vector A and a vector B in rectangular coordinates and ask you, what is the angle between those two? What would you do, Benjamin? What would you do to answer that question?
To find the angle in between them?
Yes.
Um,
So I know AX, BX, AY, BY, AZ, and BZ because I know the vectors. Now I want to know the angle between them. How do I do that?
I'm not sure.
Well, actually, you have the answer right here. Isn't the cosine of theta equal to the dot product of A and B divided by the absolute value of A and divided by the absolute value of B? Isn't that right? From that equation right above? Now, if you know the cosine of theta, you know theta, don't you?
Yes.
Because you can put in the arc cosine. This
Yes.
is an example where there's no ambiguity in the physical problem. The angle theta will always be some angle between 0 and 180. And you will always get, when you plug into the arc cosine, you will always get some angle between 0 and 180. There's no ambiguity associated with this calculation. Okay, that is the scalar or dot product. You should note a few things. Multiplication by a scalar commutes. It makes no difference if I say little a times the vector A or the vector A times little a. It means exactly the same thing, doesn't it? It's also true that scalar multiplication commutes. So A dot B is exactly the same thing as B dot A. You can see that from the formula. It's exactly the same thing. Now the next kind of a vector multiplication. Oh, what did I do? Okay, I don't know how to get rid of this thing now. There we go. Okay, now our next kind of multiplication is called the vector product or the cross product. So the scalar product is called the dot product, and the vector product is called a cross product, and that's just because of the symbols we use. So I'm going to define this in a way that seems a little funny. The magnitude of A cross B is equal to A times B times the sine of the angle theta between them. Now, I wrote it that way because the vector product of two vectors is a vector. So if I take the cross product of A and B, I'm going to get a vector. I can write the magnitude of the resultant vector as AB sine theta, but that doesn't tell me what direction it's in, does it? Sometimes this is used for formula, but in rectangular coordinates, A cross B is equal to this. Put I, J, K on the top. Then put AX, AY, AZ. Then put BX, BY, BZ. Okay, this is a determinant. It is actually not the definition of cross product. It is a mnemonic device for the cross product. The cross product is actually defined as take the fingers of your right hand, put them in the direction of A, then put your palm in the direction of B, so you can curl your fingers around. Your thumb will point in the direction of A cross B. So the vector product of two vectors is always perpendicular to both of them. And the way we use this mnemonic device is to expand this determinant. Those of you who learned the rule in high school remember how to expand a determinant, but if you don't, I'll tell you how. Start with I and create a minor by eliminating this row. The top row of this column. So that becomes A, Y, A, Z, B, Y, B, Z. Minus J. So we alternate signs. And we cross out this row and this column. You get A, X, A, Z, B, X, B, Z. Notice that for each of these minors, that the J direction does not have within it any components in the J direction. That's because you're going to end up being at right angles. Now we alternate signs, so we go plus K, and that will now be AX, AY, BX, BY. This is a pain, I know. Okay. Has anyone seen this before? No one? All right. So as I said, this is a mnemonic device for figuring out the components of the cross product. So the magnitude is A sine theta. The direction is given by the right-hand rule. But if you want to write it in components, you use this device, this mnemonic device. So how do I expand this? Well, I multiply this way, and then I subtract multiplying this way. So the ith component is AY times BZ minus BY times AZ. Now I've got minus the jth component. So that is AXBZ minus BXAZ. Now notice you've got a minus sign here, so if you want, you can do that. And now we have to add the last component, K, which is going to be AXBY minus BXAY. I think I did that right. Okay, so you can either remember how to expand the determinant and simply write this down, or you can just write down this formula and have it for easy reference. But that's the vector product of two vectors. It will always be at right angles to both of the original vectors.
I had a quick question.
Yes.
Would this be the same as the cofactor expansion theorem?
I think what you're referring to is the theorem of how to expand the determinant as cofactors. And that is exactly what I have done.
Okay.
So I think the answer is yes.
Did you do J correctly? Should it
So I've
be,
got minus J,
shouldn't it be AZ?
Well, I've got the minus sign here. And the plus sign here. I did it correctly. There's a minus sign right here. So when I this way minus this way, then with the minus sign gives me this. See, this minus sign reverses the order.
Okay.
So the minus sign, AX times BZ, and that's what I've got, minus AX BZ. That minus sign is irritating, I admit. Okay. All right. That was a lot, wasn't it? We've got a few more things that we need to discuss. Let me look at the schedule and see what's happening in our schedule. So we've already made a small change, which is that we're going to discuss the measurement and uncertainty on Wednesday. So we will have Mastering Physics Chapter 1 will be due Wednesday. That will be due at 11:59 Wednesday evening. So work on Chapter 1, Mastering Physics, and ask questions next time on Wednesday. And then you can finish it on Mastering Physics after class if you need to. Same comment with PIP. PIP Chapter 1 is due on Wednesday. So you will have to work on those problems and then ask questions during class, then complete them and upload them. So that's actually quite a lot to do. And I haven't yet set up Mastering Physics for you. I'm going to do that right after class. But you can start working on the problems because you know what the numbers are. They're the same as in the book. And I promised I'd put you the 14th edition so you can read, but that won't have the right problems. So after class, I'll set up Chapter 1 for Mastering Physics and give you the 14th edition for reading. Okay, and in general, I didn't say this, but in general, Mastering Physics and PIP are going to be due at 11:59 on the day they're due. That's not because I want you to work all night. That's because 11:59 is the default, so I just let it ride to give you as much time as you want. But please don't wait to start working on any of this until, nighttime. Do things ahead of time. Be prepared with questions on Wednesday. Okay, does anybody have anything?
Yes, I have a question.
Yes.
So, just for clarification, are PIP and then Mastering Physics two different textbooks?
Yes, the PIP comes from the University Physics Textbook 15th edition.
Okay.
Those problems are the same on Mastering Physics as they are in the book. Okay, PIP is a set of additional problems that are on Canvas. You'll have to download the file and open it up and find the problems and solve them. And write them out and submit them via Canvas.
Got it. Thank you.
Okay.
I don't know if it's just my Canvas, but when I pull up the PIP Chapter 1, it just says no details on this assignment. So is it like on files or where is it? Where like the actual
Oh,
problem?
PIP is under files /PIP. It's in there. So there's no details in the assignment because the assignment I've given you on a separate sheet. I didn't write down what the actual assignment was, except that it's PIP Chapter 1. So just for clarification, your PIP Chapter 1 problems are J4, K3, and M2. So PIP is broken up into sections with A, B, C, D for each chapter. So those three problems you're doing, J4, K3 and M2. Maybe I should bring it up just to make sure everybody is on the same page. Okay, so here we go. Problems in introductory physics. Check on that. Oh, here it is. Open it up. You might want to download it. It's a big file. It's easier to work with when you're not working through Canvas, but come on. There it is. Ooh, is it just still loading? I think it's still loading. Oh, here we go. Okay, so chapter 1. Let's go to chapter 1. Okay, so you are doing chapter 1, J4. So where is J4? Ah, there it is right there. Chapter 1, J4. Oh, they actually give you the solution. Okay, doesn't matter. Okay, and similarly for K3, there's K3 right there. Okay, does everyone understand? Okay, I'm reading the chat, but I don't see any questions in here. Someone set up a Discord. Good. Okay, I encourage you to work together and help each other. It's a good thing for you. So don't be afraid to help your neighbor. It's not like medical school. Helping your neighbor isn't going to hurt you. It's going to help both of you. Okay, anybody have any other questions? Nothing? All right. Well, then I hope
Wait,
everyone
I
has a
have
really
a
good
question.
Go ahead.
Are you gonna like record the class and then upload it onto Canvas?
No, I'm not going to record the class. Sorry. I know students want me to, but it's a trap and a delusion. There's no value to it. Come to class, pay attention, do the work, and ask questions during the next class. Just watching a video of me yakking is, even more boring outside of class. I guarantee it. So, okay. Hope you're all right with that. Anybody else?
I had another question on the exercises. So measurement and uncertainty would be, are we going to do the questions on that worksheet, or?
We're going to, in that particular one, we're going to do them together. And I'm going to go through it and explain it to you.
Okay. So should we just like read through it and then be prepared on Wednesday?
Read through it, try to do the problem. Some of them are activities you actually have to do. It was designed for being in class. So for instance, take a ruler and measure your lab table. Okay, well, you can just measure something at home and make sure you understand the thing. One of them, I asked you to make a pendulum and measure, the amplitude, not the amplitude, the frequency or the period of the pendulum. You don't have to do that if you don't want to. We'll just discuss it during class. For all the other exercises, you have to actually do the problem. and recite in class.
Okay, thank you.
Yeah, you're welcome. Okay, anybody else? Okay, well then I hope everyone has a really lovely evening, and I will see you on Wednesday.
Thank you.